Hello, this is Christina Knudsen, and this is the third video in the series on generalized linear mixed models. So in the first video, we built up the linear model to eventually get to the generalized linear mixed model. Then in the second video, we went through a couple examples, one with a log mean as the left-hand side of the regression equation, and the other one using the log odds as the left-hand side of the regression equation. Now that we understand the models, we can get into inference for generalized linear mixed models. And in particular, we're going to focus on likelihood-based inference for generalized linear mixed models. So if you haven't already watched the video on like maximum likelihood, then it will be useful to go and watch that because that pretty well introduces the topic of the likelihood. So if you have already seen it, just remember that the likelihood is a function of the parameters given the observed data. And something really important here is that we use just the observed data. We'll talk more about that in a bit. So likelihood-based inference includes a few things. It includes maximum likelihood estimation. It includes confidence intervals. It includes some hypothesis tests, such as the Wald test, the likelihood ratio test. It includes standard errors and covariances of the parameter estimates because we use the likelihood to calculate these covariances. Okay, so here's the thing about likelihood-based inference for generalized linear mixed models. The likelihood is a tricky thing. So the likelihood cannot depend on the random effects because the random effects are not observed. And we saw that the likelihood is based just on the observed data. So what we need to do is integrate out the random effects. We're going to integrate over these random effects, and so therefore our likelihood is an integral, and it's often a high dimensional integral. So for example, in our salamander example, we have 120 salamanders and each one had its own random effect, so we have a 120 dimensional integral. For kind of simple models, we're able to break down a high dimensional integral into a product of maybe like univariate integrals, but in most non-trivial generalized linear mixed models, we cannot break up our likelihood in this way. So for example, if we looked deeper at the salamander example, going into more detail than I provided already, we would see that we have six 20 dimensional integrals. All right, so if we have a likelihood that's an integral, then that means that we need to maximize this integral to find the maximum likelihood estimates, and we need to take derivatives of this integral to find the variances. So we can see that this is going to be pretty hard. It's going to require a lot of brain power, but really, even if you're super smart, it's going to require more than you even have. And it's still even hard for computers. Computers can handle numerical integration for simpler integrals, like maybe low dimensional, like 1, 2, 3, 4, 5 dimensional integrals. But once we get into higher dimensional integrals, our computers cannot use numerical integration to approximate these integrals. So what we're going to do is use something smarter than plain old numerical integration. We're going to use Monte Carlo likelihood approximation. And this is what is used in the R package, GLMM. Okay, so what is some of the statistical theory underlying this maximum Monte Carlo likelihood approximation and the R package GLMM? Well, the R package GLMM enables all likelihood-based inference. So what this means is that we can calculate the Monte Carlo maximum likelihood estimators, and they will approximate the maximum likelihood estimators. And moreover, the Monte Carlo maximum likelihood estimators will converge to the MLEs as your Monte Carlo sample size increases. Another thing, first thing that I guess I should have mentioned, is that GLMM approximates the entire likelihood function using Monte Carlo likelihood approximation. So we can do more than just maximum likelihood estimation. We can do any sort of likelihood-based inference. And one nice thing is that the Monte Carlo likelihood approximation converges to the likelihood as your Monte Carlo sample size increases. And what this means, since the MCLA converges to the likelihood, this tells us that all the likelihood-based inference will converge as well. So the one example was that the Monte Carlo maximum likelihood estimators converge to the maximum likelihood estimators as the Monte Carlo sample size increases. Okay, so even though likelihood-based inference is hard for generalized linear mixed models due to the random effects, we can do it. We can figure something out. We can use this Monte Carlo likelihood approximation. Okay, so let's go back to the salamander example and see how to use our package GLMM to fit the salamander model. So this is in R, and you can install the R package from CRAN. So first thing we'd want to do is call library GLMM, and we're going to use the salamander data. So type data salamander. And just to get an idea of what the salamander data looks like, we can do head salamander, or there's a whole bunch of other functions that you can use to check out what the data looks like. In particular, what we see here is we have 4 variables. First, we have mate, and this is our binary variable saying whether or not that particular pair of salamanders mated. So for example, 1 means yes, they did mate, 0 means no, and we can see in the first 6 entries of this data set, we have 6 successes, all 6 of the pairs did mate. All right, so that's our first variable, mate. Our second variable is cross, and remember that the first letter is for the female and the second letter is for the male. So for example, the first few entries involve 2 rough butts. This 6th entry here has a female rough butt and a male white side. Then finally, we have ID numbers for the female salamanders and the male salamanders, and we'll use these to determine our random effects. All right, so if you've used the R function LM to calculate regression equations for a linear model, we have a similar thing here for a generalized linear mixed model. So in particular, we're going to use the formula notation here. So we have the response here on the left-hand side, and then we put the tilde, and over on the right-hand side, we have cross, which is our fixed effect, which defines our fixed effects, and then we can put in a 0 here. So I put in this 0 so that we have no reference group. If you don't mind having a reference group, you can take the 0 out and just have mate tilde cross. Okay, so this first line is for defining our fixed effects. Second line is for defining our random effects. Random equals a list, and then we need to put 0 tilde female. And remember, this is for our female ID numbers. And then comma 0 tilde, or tilde 0 plus male. And remember, male represents the male ID numbers. Okay, so we have 2 kinds of random effects. We have a random effect for each female and a random effect for each male. Okay, next thing, we need to name these 2 variances. Since we have the first set of random effects is for the female salamanders, let's just name our first variance component F. And since our second set of random effects is for the male salamanders, let's name our second variance component M. All right, so now we have those first 2 lines done, and the third line as well. So we've defined our fixed effects and our variance components and our random effects. Next thing we need to do is say where to find the data. Where do we find cross? Where do we find female mate? And that's all in the salamander data set. Next, we tell it our Monte Carlo sample size. And for this, larger is better. But Monte Carlo is pretty computationally expensive, so don't go wild with this. Don't put in like a humongous number. I would say maybe to start, just to make sure that your code is running, choose a small m, like maybe even 100, just to make sure that things run. And once you know that things are running and that you've created the model in the way you would like, then you can create a larger Monte Carlo sample size, maybe like 10 cubed, and then we'll talk a little bit about how to see whether this Monte Carlo sample size is large enough in a bit. And then finally, we need to say, like, what is the family of this response? And since our response is binary, then we're going to use binomial. If this response over here was Poisson, then we would say Poisson.glmm. Okay, so we go off, we let this run, which will take a bit, and then we can type summary, and then the name of our model. And it will produce a whole bunch of output, which is too much to fit on one slide. So here's just one little snippet, and it's the fixed effects matrix. So this looks just like we see in the LM output. We have the estimate, so these would be like our beta hats. We have the standard error. We have the z value, which we get by taking the estimate and dividing by the standard error. And then we have the p-value. So this tells us whether each of these estimates is different from 0. Okay, so something that we can do is take these estimates, which remember are log odds of mating, and convert them back to probabilities. So if we take log p over 1 minus p and have that equal to, let's just do RW 0.3375, then we can do some algebra so that we can see the probability of mating is equal to exp of 0.3375 divided by 1 plus exp of 0.3375. So this is just algebra to get to here. And so we can see here are the different probabilities of mating for the 4 different types of crosses. So if we have 2 rough butts, the probability of them mating is about 75%. If we have 2 white sides, the probability of them mating is about pretty similar to the probability of 2 rough butts mating. When we have a female rough butt and a male white side, our probability starts to decrease a little bit. We have about a 58% chance of them mating. And if we have a female white side and a male rough butt, we have a pretty low probability of them mating, just 12.6% approximately. Okay, next thing we'll look at is which probabilities are significantly different.